Alright, so Lesson 8 begins the portion of this review on factoring. So first of all, we're going to go over factors and greatest common factors, GCFs.
Objectives. Find prime factorization of integers and monomials.
Find the greatest common factors of integers and monomials.
Right, here's some basic vocabulary back from elementary school. You got a prime number, whole number greater than 1 whose only factors are 1 in itself, and a composite number, whole number greater than 1 that has more than 2 factors. A prime number is a positive integer, so integer means whole number, with exactly 2 different factors. 2 is the only even prime number. So here, our first example, we're going to see if 36 is prime or composite. So what we're going to do is we're going to list all the whole numbers whose product is 36. And what I like to do when I do this is basically I'll start with 1 and that number. And then I'm going to see if 2 goes into it. Well, 36 is even, so 2 is going to go into, it goes into all even numbers, 36 18 times. And does 3 go into 36? It does 12. And 4 goes into it 9 times. Let's see, 5 doesn't go into it. And finally, let's see, 6 times 6. 7 doesn't go into it, 8 doesn't go into it, and then we get back to 9. Once the numbers start repeating, you've got all your factors. So these are the numbers 1, 2, 3, 4, 6, 9, 12, 18, and 36. Those are all the factors of 36. So since it's more than just 2 numbers, which is basically 1 in itself, it means that 36 is a composite number. Now let's look at the next one. We got 23. Is it prime or is it composite? Well, first of all, I start with 1 and 23. Let's see, it's not even, so 2 doesn't go into it. 3 doesn't go into it because I have a decimal or a remainder. 4 doesn't go into it. 5 doesn't go into it. 6, 7 doesn't go into it. 8 doesn't go into it. 9 doesn't go into it. 10 doesn't go into it. 11 doesn't go into it. 12 doesn't go into it. 13 doesn't go into it. And when I have 13 times 2, I get 26. So that's more than my number to begin with. So I pretty much went through all the possibilities. So the only factors of 23 are 1 and, let's see, 1 and 23. So there's only 2 factors of 23. So 23 is a prime number. All right, here's another piece of vocabulary, prime factorization. Prime factorization is a whole number expressed as a product of all of its factors that are prime numbers. All right, so here's an example here of the prime's factorization of a positive number of 90. So one way you may remember is, I think this is the most common method used, is your factor trees. So first of all, 99 times 10 is 90, and then I factor down 9 into 3 and 3, and 10 is into 2 and 5. Or I can just do it this way, where they're beside each other. And it doesn't really matter. Look here, I started at 9 and 90 here, and 2 and 45 here. It doesn't matter what numbers you start with. This prime factorization here is going to be the same no matter what. So the prime factorization of 90 is 9 times 3 times 3 times 5. Or it is 2 times 3 squared times 5. All right, now let's try and let's see if you can do the factorization of a negative number. But let me give you a hint. On your first branch here of your tree, when you do your prime factorization, you're going to do negative 1 times 140. All right, and then let's just go ahead and do this together. I'll bring my negative 1 down. You never stop and leave it up a level or you're going to miss some numbers. And let's see, I think since it ends in 0, 14 times 10 is a good way to go. And then I have negative 1. 14 factors into 2 times 7. 10 factors into 2 times 5. And all these numbers are prime. So my prime factorization of negative 140 is negative 1 times 2 squared times 5 times 7. And if I multiply all those together, I get negative 140. One way to check to make sure you haven't went wrong anywhere is to take at each level in the factor tree, if you multiply all the numbers together, you should get back what you started with, and your prime factorization should give you what you started with. Alright, another piece of vocabulary. Factored form. A monomial expressed as a monomial is in factored form when it is expressed as a product of prime numbers and variables, and no variable has an exponent greater than 1. Alright, so I'm going to completely factor these two, and then I have 2 at the bottom for you to try. So first of all, I'm going to factor 12 into 2 times 6. I'm going to do my numbers first. And then 2, and then 6 factors into 2 times 3. And the square tells me how many A's I have. So I have 2 A's, and the cube tells me that I have 3 B's. So my prime factorization of 12, A squared B cubed is equal to 2 squared times 3, A, B, B, B. Or I could put 2 times 3, A, and 3 B's. Alright, negative 66. So that factors into negative 1 and 66. And then 6 is 6 and 11. And then my 6 factors into 2 and 3. Alright, and then I have 1 P and 2 Q's. So my prime factorization here is negative 1 times 2 times 3 times 11 times P, and I have 2 Q's. Alright, here's 2 at the bottom. You try those, factor those, prime factorization, and then restart the video to check your answer and make sure you did it correctly. Alright, here is my prime factorization of 18x cubed y cubed, and here's my prime factorization of negative 26rt squared. Alright, another bit of vocabulary, the greatest common factor. The greatest common factor is the product of prime factors common to 2 or more integers. Alright, here's some key concepts. A GCF of 2 or more integers is the product of the prime factors common to both integers. So common means it's shared in both factor trees. The GCF of 2 or more monomials is the product of their common factors when each monomial is in factor form. So we take our monomials, we put them in factored form, and we look to see what's shared by both factor trees. If 2 or more integers or monomials have a GCF of 1, then they are said to be what's called relatively prime. Alright, so I'm going to do 2 examples, and I got 2 for you to try. So first of all, I want to find the GCF of 15 and 16. So if I factor 15, it factors into 3 times 5. So my prime factorization of 15 is 3 and 5. And if I factor 16, I'm going to start with 4 and 4. And remember, it doesn't matter how you start. Your final line's going to be the same thing no matter what. And 4 is 2 times 2, and 2 times 2, and 2 times 2. So my prime factorization of 16 is 2 times 2 times 2 times 2. And if I look at my 2 factor trees here, they share absolutely nothing in common. So these 2 terms would be what is called relatively prime. They don't have any factors that they share in common. Alright, let's look at my next 2, and we'll do my factor trees. I'm going to start out with 4 times 9. It's 36. 4 factors into 2 times 2, and 9, 3 times 3. Then I have an X, and a Y. Alright, 54. That is 6 times 9. And 6 factors into 2 times 3, and 9 is 3 and 3 again. And I have an X, and I have 2 Y's, and I have a Z. Alright, so looking for my GCF GCF, I'm looking for things each factor tree shares in common. So first of all, I have a 2 in this factor tree and a 2 in this factor tree. So they share a 2. And I'm out of 2's here, so I'm going to move on to the 3's. I have a 3 here and a 3 here. So they share a 3. And if we'll look, I have a 3 here and another 3 here. So they share another 3. Alright, now I'm going to look at my variables. I have an x here, and I have a matching x here. Alright, I've used all my x's on this one, so I'm going to look at y's now. A y here, a y here. So they both share a y in common. And that's all the y's I have left here. So there's nothing else those factor trees share in common. So this is my GCF. And GCF is greatest common factors. Factors means multiply. So I am multiplying all those together to get a GCF of 2 times 3 is 6 times 3 is 18. And they have an x and a y. So that is my GCF of these two terms, 18xy. Alright, now try these two down here and see if you can find the GCF. And restart the video when you're ready to check your GCF. So pause the video now. Alright, here's my GCF for these. If you have any questions about it, ask me in class. Alright, last problem, and it's a word problem. I know how much we all love those. Alright, so here's our problem. We have the area of a rectangle is 28 inches, square inches. If the length and width are both whole numbers, what is the maximum and minimum circumference of the rectangle? So first of all, to do this problem, we have to find the factors of 28 because they're our possible side lengths since our rectangle is 28 square inches. So we have to list our factors of 28. So 1 and 28. Let's see, 2 and 14. And finally 4 and 7. Alright, so we're going to draw a rectangle. Let's see, 28, 28 with those side lengths given. And that would give us what? A perimeter of 29 plus 29, which is 58. And we're going to draw a rectangle, sides 2 and 14. So let's see, 28 plus 4 is 32. That would be the perimeter in that one. And if it was 7, 7, 4, 4, and my rectangles are not drawn to scale, it's 11 plus 11, it's 22. So let's see, which one would give us the biggest perimeter? Would be this one, a perimeter of 58 with side lengths of 28 and 1. And the one that would give us the smallest one would be this one right here with side lengths of 7 and 4 with a perimeter of 22. And these type of problems are likely to show up on the ACT. So keep in mind how to work one of these. And that's the end.